When setting up double integrals, you've seen that sometimes you need to slice things horizontally rather than vertically. And the same sort of thing is true for triple integrals. You have a lot of different choices for the order in which you do the slicing, and sometimes some ways of slicing will be easier than others. So here we have a triple integral of a function over a region bounded by these four surfaces that are shown here: y equals z squared plus 1, and the planes y equals 5, x equals 0, and x equals 2. A good way to start is to sketch the region that you're integrating over. So again, with my usual convention for the three axes, the equation y equals z squared plus 1, well, in the yz plane that defines a sideways parabola like this, and since there's no x involved, this whole thing will give me what we call a parabolic cylinder. Now I'm capping it off at y equals 5, and then at x equals 0 and x equals 2. So you get this kind of solid shape here. Now, if we cut it in the usual way, where you do z-bounds first, what's going to happen is that your range of z-values, well, maybe it's even a little bit easier to see if I just look at the yz part for just a second. So if I go back to this parabola here, what's going to happen is that slicing in the z direction means you're going to start on this parabola and end on the same parabola, on sort of like the other half. Or in the general solid, you're starting on this parabolic cylinder on its bottom half and ending on its top half. Well, to figure that out, you have to rewrite the equation here for z in terms of y. So this is z squared is equal to y minus 1. So z is plus or minus the square root of y minus 1. So in fact, that's what the range of z-values would be in this case. And then you'd look at the shadow and kind of go from there. But that's a little bit messy. I mean, you never really feel very happy to have a bunch of square roots showing up in your bounds. So you might ask, well, is there a better way that I could slice this? Well, yes, you don't have to actually slice z first. You can slice y first, or x first. You just sort of take your pick. In this case, x first is a really easy one, because the boundary of x values, x goes from 0 to 2. I've just kind of chopped this whole thing off in the yz plane, and then in this parallel plane right here. So let's slice x first. So x goes from 0 to 2. Right? In principle, I could have had whole surfaces. I could have had x equals some function of y and z to x equals some other function of y and z. It just so happens that in this case, the functions were very simple. Now, when you go to look at the shadow, it's not the shadow in the xy plane. It's the shadow in the yz plane. And that's exactly that picture that I was starting to draw. With the parabola and this line. Right, that line again was the line y equals 5. And that parabola was the parabola y is z squared plus 1. And now you just slice this region in any way that seems useful. Well, if I slice in the z direction now, I'm going to have the same range of z values as before, and it's still kind of ugly. So let's slice in the y direction. That works out nicely, in fact, because this left boundary, y equals z squared plus 1, that's already solved for y in terms of z. So in fact, y goes from z squared plus 1 all the way up to 5. And then, for the last bounds, the range of z values, I just have to find the highest point and the lowest point. And in this case, the highest point happens at z equals 2, because 2 squared plus 1 equals 5. And the lowest point will be at negative 2. And so slicing things this way, you end up with the integral from -2 to 2 of the integral from z squared plus 1 to 5 of the integral from 0 to 2 of your function. And now it's dx, dy, dz. Remember again that the inside differential goes with the inside integral and so on. So the upshot of all of this is that when you're setting up a triple integral, it's worth spending a little bit of time trying to think about if there's a better way of setting up the integral rather than z first.